Here is section 13.3 on graphs of rational functions. This will be a continuation of what we were doing in section 13.2. You'll notice that the only difference now is that the format of our function is going to change. So just to serve you as a reminder, section 13.1, the format of our rational function was y equals a over x minus h plus k. And so now we are going to work with functions that are written in f of x over g of x format, where f of x and g of x are expressions of polynomials. Okay, so we are still dealing with rational functions. Again, the format is just changing. Notice that the rational function can have both vertical and horizontal asymptotes still if written in this format. And here's something that is being introduced to us. A rational function has branches, or the curves that we see in those graphs. And the rule is that the number of branches is determined or can be determined by the number of vertical asymptotes. So in essence, the number of branches can be found by finding your number of vertical asymptotes and then add 1 to it. So if you look in this picture right here, we have a vertical asymptote right here at probably what looks like x equals 1. And since we have one vertical asymptote, if we add 1 to it, it tells us that we should have drawn 2 branches. And notice we have 2 branches written right here. Okay, so that's just a simple additional feature that we can add to our list of things. So let's first find out how we find vertical asymptotes when given this form, okay? If you recall, let's look at an example from last section over here. When we looked for our vertical asymptotes, x equals -2, okay, which is in this picture right here, we always looked to our horizontal translation to help us depict that. So the graph had gone left 2 units. So that means our original horizontal asymptote at x equals 0 shifted 2 units to the left. That's how we would find our vertical asymptote. And our horizontal asymptote was determined by what the vertical movement was. Well, since our horizontal asymptote originally starts at y equals 0, if the whole graph went down, our horizontal has to also shift down 2 units. So the shifting down of 2 units helped us determine our horizontal asymptote. So what do we do when the format doesn't look like this? So here's what we do. So highlight along with me if you are one to highlight in your notes. To find vertical asymptotes, here's what you're going to do. You are going to set the denominator factors equal to 0 and solve. Now, before you do that, okay, first, fully factor your entire rational, okay? And when I say entire rational, I mean factor numerator and denominator, okay? So let's look at the following examples. So we have a rational y equals x minus 3 over x squared minus 9. Hopefully you are noticing right here that this is an example of difference of squares, okay? So we are going to need to factor wherever possible. Now, difference of squares told us that if we had 2 squares that we're subtracting, we can square root each of those terms and rewrite it in a minus b, a plus b form. So let's do that. Well, notice that our numerator value, there's nothing we can do with that. It's just going to stay the same. But down here in our difference of squares, let's rewrite it. Well, square root of x squared is an x, and the square root of 9 is a 3. Okay. Once we rewrite it, we notice that we have like factors in the numerator and the denominator. So those simplify, and the rational now becomes 1 over x plus 3. Now remember, in our definition, we said that we needed to set the denominator equal to 0. So let's go do that. To find our vertical asymptotes, we take x plus 3, set it equal to 0, subtract 3 on both sides, x equals -3. So for this particular rational, our vertical asymptote is going to cross at x equals -3. So it would, if this was our graph, we would draw a vertical line going through -3. Okay, well, let's go to the next problem. Let's shift my paper down a little bit more. Let us work with y equals x squared minus 4 over x squared plus 4x minus 5. So notice this here is also going to be a difference of squares problem. Okay, and this one right here, go back to your notes on factoring that we took a few days ago. This is when you are going to factor a trinomial when a is equal to 1. Okay. So pause the video right here and take some time to do the factoring of the numerator and the denominator value. And when you're done, come back. Okay, so here's what you would have done. Okay. Difference of squares tells us the square root and square root. So we have x minus 2 and x plus 2. Okay. Here our a value was an invisible 1. So our questioning technique says what times what gives me a -5 that at the same time gives me the b value of a 4. So a reminder in our notes, what we did was what times what gives me the c value of my problem, and what plus what gave me the b value of my problem. C in this case is our -5, b in our case is a 4. So the only numbers that would satisfy both of these equations would be a +5 and a -1. Okay, 5 times -1 is indeed -5. 5 plus -1 indeed is 4. So what you will do is take the answers that you found, the 5 and the -1, and put it into your factors. Notice here, no factors are reducing or canceling. So we follow the rule of finding vertical asymptotes. We look to the denominator once everything has been factored and simplified, and we set them equal to 0. In this case, we have 2. Here's our first vertical asymptote, and here's our second vertical asymptote. Okay. Moving down to number 3. Now, at times, we're going to end up with rationals where factoring is not necessary. So we can just jump straight into the problem. We look at our denominator, and we set it equal to 0 and solve. Okay. So we're done finding our vertical asymptote. But I want you to pay attention to situations that may happen, such as this. All right, you would be tempted to write, for x squared plus 2, by the way, you would be tempted to try and factor that. But this here, even though it's raised to a second power, it's not factorable. So what you do is you take that factor and you set it equal to 0, despite the fact that you can't factor it. Well, you can't factor it into real numbers. Let me say that better. But if I subtract 2 on both sides, okay, I'm going to end up with x squared equals -2. And x squared equals -2, this does not yield real solutions, okay? It would yield rather complex solutions, okay? So in essence, if you wanted to solve this, it actually would give us x equals plus minus I square root of 2. That's what that would be. These are not real solutions, and I'm looking for real solutions. Another way to explain it is no number squared will end up giving you a negative answer for real numbers, that is, okay? So this here is a no solution, no real solution answer. And because it's a no real solution answer, okay, you will tell me that there are no vertical asymptotes for this particular problem, okay? So if you recall at the beginning of our lesson, I introduced to you the little formula to finding number of branches. Number of branches is found by taking the number of vertical asymptotes you have found and adding 1, right? So let's look at this number 1. Number 1, you only found 1 vertical asymptote. So if we were to graph this function right here, how many branches would we have? Well, number of branches says that we take the number of vertical asymptotes that we have. There's only 1 that we found, and we need to add 1. 1 plus 1 gives me a 2. So I'm going to come down here and put how many branches would each graph have? Well, for number 1, there would be 2. I would like you to please go do numbers 2, 3, and 4. I'm going to give you about 10 seconds. Go. All right. So the answers to these you should have is a 3, a 2, and a 1. Those are the number of curves or branches you would draw if you had to draw these right now. Okay, moving on to the next section. Not next section, sorry, next page. Next page, we're going to cover how to find horizontal asymptotes. Okay, again, let's grab our little highlighter here and highlight the definition or the process of how to find horizontal asymptotes. And that is this line right here. To find horizontal asymptotes, you are going to compare the degree of the numerator to the degree of the denominator. The degree, if you recall from our polynomial unit, is the highest exponent in our polynomial. Okay, so you are going to find the degree in the numerator, you're going to find the degree in the denominator, and you are going to compare those numbers, okay? So let's look at this first example. I'm going to zoom in a little bit here since those numbers are rather small. Let me shift my paper as well, okay? So let's look at this first example in the upper right. So we have 3x cubed plus x minus 1. So look at the numerator value. The numerator degree value is going to be this number right here. And the degree of the denominator is going to be this invisible number right here. So we use the letter n for numerator degree, and we use the letter d for denominator degree. We got a 3 and we got a 1. N is bigger than D. And when that happens, our condition says if N is greater than D, our horizontal there will not be any, sorry, I stumbled on my words there. We will not have any horizontal asymptotes. What we are going to have are called slant asymptotes. Okay, I will not require you this year on finding slant asymptotes. So all I will need you to do is tell me that there's none, okay? But for matter of information, I want you guys to know that if your numerator is higher than your denominator degree, what you have is called a slant asymptote, okay? Now, what if those two values end up being the same as in this next example? So notice our degree here is a 2, and the denominator degree is a 2, okay? So let's write that here at the side. Our n and our d are both equal to 2. When they end up equaling one another, okay, let's highlight like crazy again. When they end up equaling one another, what you're going to do is you are going to find the lead coefficient, okay? So I'm going to use a pink here. Lead coefficient. Lead coefficient is found by finding the leading term. And the leading term is always going to be the one with the degree. We already found the degree, so let's go look for the leading coefficient. We found the degree, let's go find the leading coefficient, okay? So the leading coefficient in this numerator is a 4, and in the denominator, it's an invisible 1. So let's write that information we just found. Leading coefficient of a numerator is a positive 4. Leading coefficient of denominator is a positive 1. So because of limited workspace, I'm going to write the horizontal asymptote over here. What is 4 divided by 1? It's going to be y equals 4. And notice how I pointed to the fact that you must write y equals, okay? Always write your vertical and horizontal asymptotes in the form of an equation, okay? Please don't forget that. You must always write x equals or y equals. Okay, next, the last is when n is less than d. This is the last condition, when n is less than d. So let's look over here to our right again. Our n value for the numerator and the d value for the denominator. So what did you write? You should have written n equals 1 and d equals 2. So the n is indeed less than 2. When your numerator degree is less than 2, there is no work to be done. You just have to tell me that your horizontal asymptote is equal to 0, and you're done. So let's take what you have learned in finding horizontal and vertical asymptote, and let's apply it in the example below, okay? So let's shift this, and let's do this example. So you'll see here on the far right that I have provided a bit of a bubble to help us in the order of doing things in order to graph a rational. Now you don't have to follow these steps, but just to be cohesive with everybody, this is the order that I'm going to go in, okay? So step number 1, so I'm going to come over here and write step number 1. And the first thing is to factor the numerator and the denominator. So let's go ahead and do that. Let's rewrite our function in factored form. X squared minus 3x plus 2. I needed two numbers that multiply to be 2, that add to be negative 3. So x minus 2 and x minus 1. Negative 2 times negative 1 does end up being 2. Negative 2 plus negative 1 does give me negative 3. Okay, same thing. What two numbers multiply to be 8 that add to be negative 6? X minus 2 and x minus 4. Negative 2 times negative 4 is an 8. Negative 2 and a negative 4 add to be negative 6. So you probably see that this x minus 2 and this x minus 2 are alike. So we are going to reduce this factor even more. And we end up with x minus 1 over x minus 4. So this is the function of f of x we're going to work with. So let's go to number 2. Number 2, if I can get my pen to work. Oh, goodness. You will go ahead and write number 2, and let's see if I can get it. Here we go. Number 2 asks us to find wholes, or whole, okay, depending on how many factors cancel. Wholes are dependent on when factors cancel. So notice above we had these factors cancel. When that happens, know immediately that's going to be the x-coordinate of your whole. All right, so you take what you canceled, you set it equal to 0, and you solve for x. That's the x-coordinate of your whole. So basically you're at 2 comma question mark because you just found the x-coordinate. Now I need to come over here and find the y-coordinate. How do I do that? Well, I take my x value and substitute it back into my equation, which is this one right here. So let's go do that. F of x is 2 in this particular step. Replace that x with a 2. Replace that x with a 2. And I'm left with 1 over negative 2. So what does that mean? That my whole occurs at 2, comma, negative 1/2. So let's come over here and plot the whole one time. So 2, comma, negative 1/2. Well, 2, comma, negative 1/2 means go down half a unit. And it's going to be kind of hard and tight, but do your best to draw an open circle right there. Okay? So not a filled in dot, but an open circle as best as you can. Okay? So there's our hole in our graph. Step number 3 now tells us to find the x-intercepts. So come over here and let's go do that. Now, to find the x-intercepts, what I need you to do is you take your numerator factors or factor, okay, and set them equal to 0 and solve, okay? So we go back to our function right here, and our numerator is our top value. So we take that x minus 1 and we set it equal to 0. I'm having a lot of issues with my mechanical pencil today. X minus 1 and set it equal to 0. And then I'm going to solve that expression by adding 1 on both sides. And now I have my x-intercept. So I'm going to box that in here. Okay, I'm going to box this here so you know all the stuff that you found for each step. Okay, so x equals 1, so x-axis, x-intercept. So let's put that dot right there. So we have 2 dots plotted. Number 4. Number 4 says find the y-intercept by letting x be 0. So y-intercept, even though it's written over here, I'm going to still do it again. Let x equal 0. So when we knew x was 2, we solved it. Let me pause this a second. Okay, I think the announcements are done. But anyway, when finding y-intercept, you let x be 0. So what you do is, just like we did over here when we knew what x was and we substituted into our function, we're going to do the same thing with our 0. So go back to your function equation, replace every x with 0. So f of 0 equals, replace that 0, that x with 0, and replace that x with 0. 0 minus 1 is a negative 1, and 0 minus 4 is a negative 4. Well, those negatives reduce to 1/4. And upstairs main hall. Unfortunately, I had one more announcement. Alrighty, so our y-intercept then is going to be at 0, 1/4. So let's box this in as another answer and another characteristic that we get to plot. Okay, so there is my 0, 1/4. Need to be a little bit closer. Okay, there we go. Okay, number 5. Number 5 now is find all the vertical asymptotes, which we spent just now on the first page of our note-taking guide working out, right? So vertical asymptotes are the denominator factors, okay? So denominator factors, or factor, where you set them equal to 0, okay? I'm about to go old school and use a different pencil, I swear. Okay, so let me zoom out a little bit here so that we can see a little bit more. So if we look at our reduced expression here, the only factor we ended up having in the denominator was x minus 4. We just had 1. We didn't have more than 1. So we take that denominator factor of x minus 4 and we set it equal to 0, add 4 to both sides, and that is our vertical asymptote. So let's come over here and let us draw a vertical asymptote at x equals 4. And we use dashed lines. And now let's proceed to find our horizontal asymptote. The horizontal asymptote, we compare the numerator and the denominator degrees. Okay. So we look at the original, function, okay? So I'm going to put over here, look at original, I can't spell. Look at the original unfactored rational, okay? So let's scoot our paper down a second. I'll come back there. Let's look at our original unfactored rational. I was going to say fraction. So here and here were our polynomials. Notice that this and this were our degree values. Let me highlight it here. Our degree was a 2 and our degree was a 2. And then what do? We always look to the front of that leading term to find our leading coefficient. And in both cases, our leading coefficient, let's do it in pink, is an invisible 1. An invisible 1 and an invisible 1. Okay, so let's go back south. And let's drag this back down. So what do? Well, I've identified what my numerator and denominator degree was. They were both a 2. And I noticed that they both were equal to one another. So that means when I find my horizontal asymptote, I take the leading coefficient upstairs and the leading coefficient downstairs. So my horizontal asymptote is going to be simplified and it ends up being y equals 1. So y equals 1 says to come here, we need to draw a vertical asymptote. At y equals 1. And you can see that we have enough points already here to connect our dots. To make our first branch. But because we have one vertical asymptote, we know that one vertical asymptote means we will have number of branches will equal 1 plus 1. We should have 2 branches. So I know one branch is here. I know the other branch has to be here. Just to be a little bit more precise as to where our dots are going to be located in this section. Well, since I know it's going to be in this section, I know my values have to be greater than 4. So when x is 5, what does that tell us? Well, let's bring this down a little bit here. Okay. So let's say if f of x has an x value that's 5. Well, if my x is 5, as I'm showing you here in my notation, 5 minus 1 gives me a 4. 5 minus 4 gives me a 1. 4 over 1 is 4. So my point is 5 comma 4. So 5 comma 1, 2, 3, 4. So I can put a dot here. I can do it again. Let's do f of 6. F of 6 would be 6 minus 1 is a 5. 6 minus 4 is a 2. Well, that's about a 2.5. So 6 comma 2.5. So 6, 1, 2.5. And since we're here this far, let's just do f of 7, right? 7 minus 1 is a 6. 7 minus 4 is a 3. 6 over 3 gives me a 2. Oh, that's a nice number. 7, 2. And so you can see the curve nature. So this is going to go exponentially to positive, and this is going to decrease and get exponentially close to our horizontal asymptote. So there is our final graph of the rational function given to us today for our first example. So what I would like you to do next is come over here, and I want you to work out this problem, example number 1, on your own, okay? I need you to factor and follow the example that we just did. Note that you're going to use different factoring techniques in this problem though. Notice that this one right here, you are going to need to use your greatest common factor method. And notice that this one right here is a trinomial when a is not 1, okay? A is no longer 1, okay? So if you can't remember how to factor a trinomial when a is not 1, go back to your factoring notes to remember. So pause your video here, because the next time you hit play, you will see the answers to how this problem was worked out, okay? For your worked out example 2, just go to your note-taking guide key that you can find in Google Classroom. All right, at this time, go ahead and pause your video now. Okay, so now that you have completed your problem, here is the answer to example 1 that you worked out on your own. Okay, so right over here, notice that to factor this trinomial when a is not 1, you have to go through the process over here. So here's all the work. It's called like an AC method. So rewrite it in group. Your factors canceled here. That led you into the hole for x equals 4. Then we had to find the y coordinate. So 4 comma 12 ninths. And over here, 12 ninths is approximately 1 3/9 or 1 1/3. So that's why we went 4 comma 1/3. So 1, 2, 3, 4, 1, and a little bit higher. So anyhow, let me know if you have any questions. Thank you for watching.